Thank you. So, good afternoon, and many thanks for inviting me to give a talk in this very nice and historical place. I am a mathematician, but I am strongly interested in physics. During the recent years, I've been working on quantum information for infinite systems. So the main tool are operator algebras. But today I will talk about my last paper. It's regarding communication theory, which is not strictly quantum information, but it makes use of my experience over the recent years. As I said, I am a mathematician, so I think if you have any question, something that I say might be trivial, something that I say could be obscure. So in that case, just stop me, ask me question, no problem. I have chosen this subject not only because it's my last paper, but it's a very general paper. So the argument is very, very general. So the general point is the following. In a signal theory, if we transmit a signal, let's say we can codify the signal in a function that depends on time. No? So Alice sends a signal to Bob. And of course, Bob can receive the signal only for a finite interval of time. Not. On the other hand, the device will cut frequencies. So only certain frequency on an interval of frequency can be measured by Bob. So this has to do with a problem that all of us have had, that if we have a function with compact support and the Fourier transform has compact support, then the function must be 0. So this looks a bit paradoxical, because when we transmit, we are able to transmit signals quite faithfully. You know? For example, when we listen to music, we don't feel any cut. The problem is that mathematics is a model, and if let's say we have a function, we have a number which theoretically should be 1, but in practice, in practice should be 1, but theoretically it's 0.99999, and then we don't feel the difference. This problem was studied in the 60s, at the beginning, at 1962, by Slepian and collaborator Pollack and Landau. Landau is not physics. It's a Bell's laboratory. The problem is that we want to maximize, so takes a function with a normalized L2 function, the L2 norm is 1, and then we want to maximize simultaneously the L2 norm on an interval -1, 1. This B later will be the unit ball. No? For the moment, we are in the one-dimensional case. So we want to simultaneously maximize the function, the L2 norm on the interval, and the L2 norm of the Fourier function, the Fourier transform on the interval. Of course, because of what I said, it is impossible to get a function which is 1 and 1. No? But we can do as better as we can do the best we can, and it's called the concentration problem. So this problem is, of course, appears in many places in mathematics, in physics, for example, in Heisenberg uncertainty in principle is a manifestation of this problem. We have this uncertainty because we cannot find such a function. And in quantum field theory, for example, it was studied by Jeffy and others, but they had what they tried to do, what they did, just to find a function with compact support such that the Fourier transform decays as fast as possible. But in the 60s, in 1962, to be exact, there was this paper by Slepian and Pollack, and in the same issue of the Bell's Laboratory Journal by Bell's and Landau, that studied the so-called truncated Fourier transform. So we take a function, f, and we multiply by the characteristic function of the interval. Then we take Fourier transform, and we again multiply by the characteristic function. So essentially, we have a map from function on the interval in other function on the interval. And it's called the truncated Fourier transform. EB now is denotes the L2 projection on L2 of the ball, which is just the multiplication by the characteristic function. And F is the Fourier transform, which is, of course, unitary in L2. And if we restrict, as we can for our discussion, but not strictly necessary, if we restrict on even function, it's an involution. The square is 1. No? It coincides with. And then it is a truncation. And of course, this truncated Fourier transform defines a function on L2 of the ball, which is an integral. And the problem is to study this operator. Or equivalently, since we have the C-star property of the norm, no? So if you take FB star, FB, the norm is equal to the norm FB square, we can study, they studied the angle operator, so with the square of the modulus of the truncated Fourier transform, which takes this form. It's a product of three projections, of two projections. It's EB, the Fourier transform of EB, where he had EB is just the projection onto L2 in Fourier transform. And this is has the advantage to be a positive integral operator. It is an Hilbert-Schmidt operator. In fact, it is a convolution operator with the kernel given by the Fourier transform of the characteristic function of the interval in one dimension. It's a sin x over x. And one has to study the eigenvalues of this. So if we find a function, an eigenfunction with eigenvalues very close to 1, then it's a good concentration. However, this analysis is not easily doable. It's not easy to treat the problem in this way directly. However, something happened, the lucky accident. So Slepian and collaborators realized that the truncated Fourier transform, so also the angle operator, commutes with a differential operator, which is just the operator that I write here. No? So it's a sort of Laplacian with where we insert this parabolic distribution, and then there is a perturbation. So if x squared were not there, this would be the Legendre operator. So it's on L2 of B, it is a bounded perturbation of the Legendre operator. So they compute this the eigenfunction, the eigenvalues at multiplicity 1. So this operator shares the eigenfunction with the angle operator. So the spectral analysis of this Paulate operator is perfectly equivalent to the analysis of the truncated Fourier transform. This is called the Paulate operator. It's a classic operator, although I must say that I didn't notice operator up to last year. But it arises, for example, by separating the three-dimensional scalar wave equation in Prolet spherical coordinate system. So it's known since 1 century and even more. So this, however, this lucky accident was discovered with a surprise, and there was no conceptual understanding why, so no a priori reason. So even in subsequent literature, it was referred as a lucky accident, sometimes the miracle, and nobody could give for 50 years an explanation of why. And I would try to give an explanation in this talk for why this operator is the meaning of this operator and why this operator has a meaning that should commute with the angle operator. Now, Alan Kohn raised new interest in this Prolet operator recently. In fact, there is a very recent paper by Kohn and Moscovici on Proceedings of the National Academy of Science, where they discovered that, okay, if Slepin and others studied the Prolet operator on L2 of the ball, no? Kohn studied the Prolet operator on the complement, still has discrete spectrum, and the asymptotic of the spectrum is the same of the one shared by the zeros of the Riemann zeta function. So Kohn is interested in the Riemann zeta function. In fact, Alan Kohn was already interested in this, but the paper came recently. So I was attending the talk online by Alan Kohn. I have nothing to say about the Riemann zeta function, but when Alan displayed this Prolet operator, some light switched on in my brain because I recognize something that is familiar with me. And this will be related to the modular theory and quantum field theory. And to have this link, it's better to generalize the Prolet operator in higher dimensions. So we take the radial coordinate, and I write the Prolet operator in this way. There is one paper by Slepin also in higher dimension, but the analysis is extremely limited. I think there is a lot to understand on this higher dimensional Prolet operator, which on the other is more interesting to me than the one-dimensional case. So what my goal is to interpret this operator as an entropy operator. So an operator whose expectation values are entropy. So entropy that will measure the concentration. So it will measure the concentration as well as the integral operator. That's what I have in mind. Okay. Now, let me give a super quick introduction to the Tomita-Takesaki modular theory. So when we have a von Neumann algebra, so von Neumann algebra is an algebra of operator, bounded operator, linear operator on a Hilbert space, which is closed with also with the respect to the adjoint operation with identity. And maybe we change the representation, but we can assume that if we have a state, a positive linear function, which is continuous in the weak topology, let's say, then it is the expectation value by a vector, let's say omega. So when we have a vector, we can assume this simple fact in operator algebra that this vector is if this state is faithful, that this vector is cyclic and separating. So if we apply all operator in the phenomenon algebra to this vector, we get something dense, and this injection is one-to-one. Okay. So this means that we can identify as a linear space the phenomenon algebra with a linear subspace, a dense linear subspace of the Hilbert space. Just take an operator and we take the value of this reference vector omega. Now, what happens that the star operation on the phenomenon algebra is isometric, of course. But when we see this star operation at the level of the Hilbert space after this linear identification, this star operation, antilinear operation, is not any longer isometric. However, it is a closable operator, dense, antilinear, closed. We can take the polar decomposition. So J is called the modular conjugation, and delta is the square of the modulus of S. So J is unitary, anti-unitary involution. Delta is a positive non-singular operator, and the striking fundamental fact is that the logarithm of delta generates a one-parameter group of unitaries on the Hilbert space that implements automorphism of the phenomenon algebra that are called the modular automorphism, while the modular conjugation makes a reflection between M and the commutant. The commutant is the phenomenon algebra consisting of all operators that commutes with all operators in M. No? So a phenomenon algebra and commutant by, this is already well known by the fundamental theorem, density theorem of phenomena, the double commutant theorem. They play a symmetric role. So we have this very general structure. So you have a dynamics. We have a one-parameter group of automorphism. So in evolution, it comes exactly from nothing. So we have just a linear. No, when we are in classical terms, we always put an Hamiltonian by ends. We write the Hamiltonian. Here we have the state, and then the evolution is intrinsically associated. There is an intrinsic evolution associated with the state. And this evolution is characterized by something that comes from physics, the Kubo-Martin-Schwinger equilibrium condition. This was a work by Hage, Hugenotz, and Winnick. So if we have a sister algebra, so just an algebra operator, not necessarily close the weak topology, and then if we have a one-parameter group of automorphisms that satisfies this condition, it means that the state is not a trace, no? So a trace would be phi of xy equal to phi of yx. But we can change x and y by analytic continuation with respect to this one-parameter group automorphism. So this expectation value, for any given x and y, this expectation value should have an analytic continuation. So then when we make the analytic continuation in the strip imaginary part between 0 and beta, we make from one point to the other of the boundary, we just interchange. No? Beta is the inverse temperature in statistical mechanics. So if we have Gibbs states, it's a simple exercise that it satisfies this. But the great property of this is that it does not need a trace. There is no trace, just no Hamiltonian in. It's just so it works at infinite volume where we don't have the evolution is not in and the trace does not exist. So Takesaki realized that a one-parameter group satisfies this KMS temperature with beta equal -1, this convention, if and only if it is a the modular group. So since the very beginning, it was manifest that modular theory should have been important for physics. The generator of the modular operator is called the modular Hamiltonian, and nowadays it's well studied in physics. There is a simple generalization where instead of embedding the von Neumann algebra in the Hilbert space by choosing one vector, we choose two different vectors. So the star operation, when we take this operation, we change also the vector, and then we get a modular operator that depends on two vectors, and it is also modular, relative modular Hamiltonian, and it's well studied in physics. The reason why that is relative modular Hamiltonian is quite important for us will be clear in a moment. So let me now make a quick introduction to entropy. We have already seen, I think, yeah, entropy, of course, is a physical quantity, but I'm talking, as in previous talk, about information entropy. No? So if you have a finite set of events, a finite probability space, so each event, the event xi occur with probability pi, then the information carried by the element pi is the logarithm or proportional to the logarithm. Why? Because the probability of an independent event is multiplicative, and information is additive, so it should be proportional to the logarithm. So we take the average information, and it is called the famous Shannon entropy. The relative entropy comes from the fact that when we measure, maybe we don't, we get something slightly different. So we take in the average in the first state of the difference of the information, and it's called the relative entropy. In my view, this information relative entropy is more fundamental than entropy, but I will come back to this. Now, what are the versions of this entropy notion in quantum field theory? In quantum theory, the quantum version, the Shannon entropy becomes a von Neumann entropy. So we have a state with density matrix given by rho, and then the von Neumann entropy is the trace of rho log rho, and the relative entropy becomes the omega k entropy, the relative entropy, which is exactly given by the trace of the first entropy density and the difference of the two, the logarithm of the two density matrices. Oh, now, so far, this is quantum mechanics, if you want. So we have a trace, no? We have this, the von Neumann and omega k are non-commutative, but still we have some commutative in the sense that we have the trace. And under the trace, everything becomes commutative. But at infinity system, there is no trace. Yet, it is possible to define the relative entropy. The relative entropy, and this was defined by Araki long ago. So the entropy between two states, normal states, is just the expectation value of the modular Hamiltonian in the second state. And it's again, it's an exercise to see that in the type 1 case, where we get the omega k relative entropy. And it's quite, this has the virtue that it has all the good property, positivity, it's monotone, and so on, and it exists in general. So I share the view that relative entropy is the key notion, the fundamental notion. For example, even for Neumann entropy, there is a simple formula that I don't write, can be written in terms of a relative entropy. So we can do everything with this relative entropy. Now, I will go now in a very, very general setting. So if you want, you may forget what I said so far, then we come back. So now I enter in a situation very general where we have simply a complex Hilbert space and a real linear subspace. Very general. Of course, we can always assume that this real Hilbert space is closed, otherwise we close. Now, when I give you a complex Hilbert space and a real closed real linear subspace, I give you 4 real linear subspace because there is the real orthogonal. I can multiply the Hilbert space by I, and I can take the real orthogonal of IH, which is called the symplectic complement. No? The symplectic complement is the space of a vector, such that the imaginary part of this vector with any vector in the original space is 0. And a standard subspace means that H is closed, real linear, which is both cyclic and separating, in the sense cyclic means that the complex span of our space is dense, and separating that it contains no complex linear subspace except 0. Of course, it is very general, because if it is not so, we replace. No, if it is not cyclic, we redefine the Hilbert space, the ambient Hilbert space by the closure of this, and similar with the other. No? So we can always assume this fact. But when we have a standard subspace, then automatically we get an anti-linear operator given by this form. No? So S is the operator, this will be Tomita operator, the psi plus IH to psi minus IH. No? It is a densely defined, it is an involution, and it turns out it's closed operator. The adjoint of this operator associated to H is the S operator associated to the symplectic complement. And then we can take the polar decomposition of this S operator, and we get anti-linear, anti-unitary involution J, the modular conjugation, and the modular operator, which is delta. It's the square of the modulus of S. And delta is equal to S star S. And the property that satisfies that you have J is anti-commute with delta, and delta del modular Hamiltonian generated one parameter group that leaves our Hilbert space globally invariant, and J maps the standard subspace into the symplectic complement. No? So if we were in the situation where with our phenomenology M, we could take the self-adjoint part, the vector, close, and we have a standard subspace, and the modular conjugation, modular operator of this standard space are exactly the modular operator of this. This does not mean that this is extremely easier than the original Tomita-Takesaki theory, but it does not have the full information, because I'm not, this argument does not prove the full Tomita-Takesaki, but it proves a sort of one particle Tomita-Takesaki theory, which can be proven in half page, and so if you try. So it's very, it was known, it has been known for a long time, but never emphasized. So it came by proving theorems and so on. No? It's an instrument, but not emphasized in itself, while I feel that it is important in itself, because it makes contact with the many places, because it's very, very general. And now I have to explain the notion of entropy of a vector in a Hilbert space with respect a standard subspace. So with respect to a real linear subspace, as before, we can always assume that the real Hilbert subspace is a standard. So what I want to do, given, so what I give you, what we have is a complex Hilbert space and a standard subspace. then we pick up a vector, and I want to define the entropy of this vector k with respect to the standard space. And I give the formula, and then I will explain. The formula is given in this way. It's it's an imaginary part of the expectation value k, and pH, AH is minus I times the modular Hamiltonian, or if you want, the expectation values of the adjoint of pH log delta, where pH, what is pH? That I have to explain. So it's the unbounded projection when we take H, the span, the direct sum, but as a vector space, H plus H prime, which is not the full Hilbert space, to H, we project. We get a projection, it is unbounded, but it's a closed projection that we can plug in. So just to simplify, assume first the K belongs to A, to the standard space. So this pH does not exist. So it's just the expectation value of the modular Hamiltonian. In general, first we project with this unbounded projection to the subspace, and then we take the expectation value by the modular Hamiltonian. Now, it turns out that this projection is given by modular data, as an expression where we can write this in terms of the modular operator and modular conjugation. For example, this is important for various things, but among others, the fact that this, as I write this here, we should have, if H and H prime has a non-trivial intersection, it's not well defined, but if I define this way, it is well defined. For example, we don't need this, but it is important for computation and so on. To give just an idea, there are often the case where the modular operator is not a geometric object, so we are not able to describe geometrical, but the cutting projection is geometrical. And the cutting projection has the same modular information. So it's better to work with the cutting projection, and then so it will be in our setting just a multiplication by the characteristic function. What are the properties of this entropy of a vector? All the properties that you can expect: positivity, monotonicity. So if you take larger space, you get a larger entropy. So it's lower semi-continuous. So if you have it's a continuity in the monotone sense. So if you have a union H, it's generated by increasing sequence of subspace. We have a continuity, and it's smooth. It's finite on a dense set, for example, but not necessarily on the domain of the modular Hamiltonian. So it is something that all the properties that were, let's say what we have in mind is that we have H is our phase space, let's say, of function, and the standard space is associated to a region. No? So we want to end up with the entropy of a vector that maybe a wave would contain in a certain region. No? This is what I have in mind. So this is what I said, that pH is maybe geometry. No? So there are three things that they have essentially the same formation. They have this interplay: the geometry of the space, the modular data, the complex structure, and with cutting projection we shall end up in quantum field theory. But only this is the bridge, the cutting projection, which now you may wonder how we arrive at this notion of entropy, because of course when we have this real linear space, we can form the sister algebra of the canonical commutation relation. So the while operator that commute up to a phase according to the while relation, And we can take a quasi-free state, the state on the while operator, we have E2 minus alpha is the real part of the imaginary, of the scalar product. And so we have a sister algebra, we take the GNS projection, we get a von Neumann algebra, and then that we can identify the GNS Hilbert space with the Fock space, and then the entropy of the vector phi with respect to this real linear space is nothing but by Araki's relative entropy in second quantization of the relative entropy between the vacuum vector, this quasi-free vector, and this quasi-free vector modified with the automorphism implemented by the while operator. The automorphism implemented by the while operator associated with phi. No? So this is the link. So when we compute in first quantization, automatically we get also a computation in second quantization. Now, coming back, we can rewrite the entropy of a vector with respect to the space H, the entropy of K with respect to H, just an expectation value with this operator. No? This is just the formula that I have given earlier. But here I'm putting the emphasis on the fact that there is an operator, this entropy operator. I think this is new. I've never heard of an entropy operator. Entropy is a scalar quantity, but here it's an entropy operator. It's a real linear, it's not complex linear. It's a real linear, but self-adjoint with respect to the real part of the scalar product, positive, and the expectation values are the entropies. So I call this an entropy operator. And taking for, if we define an entropy operator as an operator like this, we can wonder what are the other possible entropy operators that we can encounter. Of course, there are simple operations. For example, apart from R, we can take direct sum to entropy operator. So again, an entropy operator. Or we can restrict an operator. It's an entropy operator. We can change the metric. So if we change the scalar product and the operator in such a way that the expectation value are the same, again, it's an entropy operator because the expectation value are entropy operator. The sum, the difference, and I will put even the entropy operator. So the integral, the L2 norm, no, as you know, in quantum mechanics, it's a Born probability. So I consider this as being proportional to the entropy. No? So all this kind of operators, I regard this as entropy operator. So also their linear combination. Now, what is the situation that we have in quantum field theory, especially for a free quantum field theory, in first quantization? First quantization, the absent situation is the following. The Hilbert space, how do we construct the Hilbert space? The Hilbert space is a direct sum of two real linear subspace. Typically, there will be the Schwarz space of real function. Then there is a real linear map from one space to the other with certain compatibility property that makes, they are such that when we modify this bilinear form, these two Hilbert spaces are in duality, we get a scalar product. So we have in reality with this real Hilbert space, this real linear space, a real Hilbert space, we can complete and we get the direct sum of two real linear Hilbert space, and we have a symplectic form defined this way, and a complex structure. No? If this mu will be if we define it this way, we'll mix the two components by the square of I is -1, so this Hilbert space will become a complex Hilbert space. That I will give you explicitly in a moment. And the standard, suppose that we have now the direct sum of two real space, the cutting projection will be also a direct sum, and the modular Hamiltonian, the logarithm of the modular operator is, well, I times the logarithm of the modular operator is off diagonal, as this form. And so when we write the entropy of a vector, in this case, in the pair Fg, it will be the sum of two operators, two entropies. The first is given by fields and the other by momenta. So we have two notions now of entropy, the field entropy and the momentum entropy. So we started with one notion, but in this situation, we have a notion of field entropy and momentum entropy. Now, let me go to another point where this previous work with Ciolli and Ruzzi, where we studied the information contained in a wave, in a solution of the wave equation. So this looks similar to what I said, but it's different. There is no Fourier transform here, no? But I'm considering a solution of the wave equation. So a wave equation is characterized by the Cauchy data, so by a pair, and we have the stress energy tensor that gives the entropy, in particular the energy density, but the problem is to define the information on the entropy, and by the previous, using the previous idea, one can do, we can define or explicitly what the structure that I said, so that in Plety form, the complex structure, the local subspace, so this real linear subspace associated to a region, the local entropy, and compute. So what we do, we have to do to define this complex Hilbert structure, complex scalar product on the solution of wave equation, which is just a pair of a Schwarz function, real Schwarz function, to have a real Hilbert subspace associated to a region, and this will be I would say that a wave is localized in O if the Cauchy data are localized in O. And then we have already the notion of local entropy, and the problem, of course, we have to compute. But now everything is explicit. This mu operator is a square root of the Laplacian. The two spaces are the Schwarz function. The symplectic form is the energy form. And then if we make we can make the computation because we need just to compute the modular Hamiltonian, but the modular Hamiltonian, the modular operator, modular group was known since 81 by a work by Peter Isloff and myself. It has a geometric meaning that I don't describe because what we need now is a modular Hamiltonian, not the modular group, which is a computation, of course, but it's much more recent. And if we compute, these are the formula for the entropy. So the entropy of a wave in a region, or let's say in a ball, is given by this integral of the stress energy tensor with respect to this parabolic distribution. And so we can do, and then there is this other term, which D is a scaling dimension of the field. This for mass zero, for mass positive mass, it's open problem. I don't dwell to that. So now coming back to the prolate operator, we have this is the prolate operator, which I consider this as a perturbation of the Legendre operator, and I define this. But I write this in this way, no? Pareto operator is L is this part here, which is the Legendre operator here. And instead of writing R squared, I write 1 minus R squared, the parabolic distribution, and then I subtract 1. So L plus M minus 1. Why? Because these are the operators that the associated to the modular Hamiltonian. So this, now what are the properties of this? That is the Pareto operator, this commute with the Fourier transform, first of all. And any linear combination of L and maybe I don't know whether maybe I should write the formula for the modular Hamiltonian. I don't know. The modular Hamiltonian for the unit ball is given by M and L minus D. So it is 2 pi I the modular Hamiltonian. So M is the multiplication by R squared. L is a Legendre, is delta 1 minus R squared, the gradient. It's a Legendre operator, and D is the scaling dimension. So these two operators, M and delta, up to a constant, which is not significant here, are the two components of the field operator and the momentum operator are given by the Legendre operator, and that is parabolic operator. Now, M commutes with the Fourier transform, and it has a nature, but when we look at this Pareto operator only on the Schwarz function, it is not self-adjoint. It's Hermitian, but not self-adjoint. So in one dimension, this was noticed by Alan Kohn. It has a defect indices 4, 4. But it has a natural Hermitian, it's in fact the minimal Hermitian extension that commutes with the orthogonal projection, and this still commutes with the Fourier transform, but this extension commutes also with the projection EB and the Fourier transform. So it commutes with the cutting projection. So the point is in a higher dimension, what one has to do is to enlarge the Schwarz operator with this way. So we consider also function which are smooth on the ball and zero outside, and Fourier transform of this function. And the natural expansion for the Pareto operator is this one. Of course, we want that it commutes with the projection in both on space and in Fourier transform. So once we do this, it is not trivial, but not difficult. It is a Hermitian operator, and the angle operator is associated with the truncated Fourier transform, and it has the angle operator TB has eigenvalues, Hilbert-Schmidt eigenvalues, which are decreasing. They go to 0, and when we look at this on the L2 of the ball, the negative of the Pareto operator is a positive, strictly positive operator on L2 of the ball. So the entropy operator now we can write in this way, no? By the formula that I wrote here, no? The entropy operator in L2 is given just by the Legendre transform operator up to plus a constant, and the parabolic multiplication by the parabolic distribution. So these are the formula for the parabolic entropy and for the Legendre entropy. I have explicitly for. And so the Pareto operator now is a linear combination of the Legendre entropy and the momentum entropy. The global formula is the following. This is the formula for the Pareto operator. The point is that the Pareto operator is it's a linear combination of the Legendre entropy and the parabolic entropy, plus, if you want to add the constant, the Born entropy. But it is up to trivial multiplication, so add the constant and multiply it by a constant. It's the unique operator with this. Now, of course, we can always add the constant or take an operator of proportion. So the Prolet operator is the only entropy operator which comes from this operator that we have uncovered, so the Legendre operator, the moment operator, and the Born operator, which commutes with the truncated Fourier transform. In the one-dimensional case, of course, the multiplicity of one, the multiplicity of the eigenvalues, so we can order the eigenvalues of the Prolet operator on L2 of the ball in an increasing order, and this was already proved by Slepian. There is an inverse ordering relation. So alpha 1 corresponds to lambda 1, alpha 2 with lambda 2, and so on. This is still open in higher dimension, but I'm quite sure that it holds also in higher dimension. So there is so said in another way, the truncated Fourier transform is a function of the Prolet operator. Which function, I don't know. And it's also a very interesting problem. But of course, so they have the same information. No? One is a function of the other. So the Lackey's accident comes from this fact that we are essentially talking about the same operator. There are two operators. One is a function of the other, and so it's clearly they commute. And I think this gives a conceptual understanding, or at least a part of the conceptual understanding for this Lackey's accident. I think I will stop here. Good. No, because there is no notion of inner automorphism. So it's not, this kind of property is not visible. In fact, it is not visible. Also, the notion of a relative modular operator is not visible. No, we have this depends only on a vector and on a standard subspace. So I call this entropy. Maybe also another name would be good. I don't know. In the sense, it is certainly a measure of information, and it's linked to some Arrakis entropy. But what is the true meaning? It's still to be understood, I think. No, so it's a general notion that I think we should look at more situation to have a better understanding. So no, concerning your question, no, there is nothing. Compact? Complex polarization of total space, complex spaces. Well, not well. Of course, the most trivial situation where you have a complex Hilbert space and a real Hilbert space, one is the complexification of the other. Then this is just the situation where everything is trivial in this case. No? But when the interesting case when you have a Hilbert space, a real Hilbert space, and then you put some complexification, which is not the standard one. No? So we have some isometric involution with square is minus 1. So you may define this is what, for example, in geometry is usual to do. No? So it's I think it's the same information. So there are several things that, in principle, have the same information, but this is, if you want, it's a manifestation of the complex structure, if you want, rather than polarization. This is but as I said, I myself, I would understand in other cases of the structure to be more. For example, there is an application of this by very recent work by Detlef Buchholz and Klaus Freudenhagen, where they studied the arrow of time, no? And they take as a measure of information this entropy, and it works very well in their concept. No? But we have to wait for being to understand better, to a better understanding.
Please. In the list of properties that the Iraqi entropy had, is there something like a strong subadditivity that if you take some of a tripartite system, I mean, usually it's sort of expressed in terms of tensor product, but now it's sort of conventional computing, some computing operators, trace of one no.
No, this is a good question. I have no translation of this subadditivity in course, but there should be, but not. But there is some mysterious fact, let's say. Araki's entropy has a lot of information. Let's say the main properties are positivity and monotonicity. They are both extremely powerful. They contain, of course, also subadditivity and so on. But if you want to prove monotonicity, it's very hard. So the general proof goes to Kosaki's formula. And in this context, monotonicity is also extremely powerful, but I have no direct proof of monotonicity. I have to go to Araki's proof that goes to Kosaki's proof. So it contains a lot of information, but it's quite unreasonably difficult to prove. So this, I think this question of your kind fit well in this framework, how to see it. Maybe once you do, I think you gain a lot of information, but it's not a real fact. It's not just rewriting.
Please. Is it still true that the entropy of your state vanishes? Repeat the question.
The question is it true in this setting that the entropy of a pure state vanishes? I'm not considering pure state, because when I say standard subspace, I'm talking about faithful state. Of course, if I remove the notion of standard, as I said, it is possible, then it is true, because you get trivial subspace, then it's okay. But for simplicity, I always put myself in the standard subspace setting.
On a general note, I was wondering whether you foresee applications to the study of deep learning or geometric deep learning, where these kinds of relative entities.
I am too ignorant on this, but I expect applications in several directions. But if you say, if I have an intuition of what could be in the setting that you say, because I'm not familiar with the setting, I would say. But it's so general that any time, I think we all more or less can produce Hilbert space and real linear subspace, So we can, for example, I gave recently a talk at Victor Katz's birthday, And then there was an initial question on how, in the framework of vertex algebras, for example. Still, we have not, but this is just an example, no? We should try.
Let's thank the speaker.